every 11-year-old in the country into a school so that there's just the right number of students in each school is really, really hard. So there's examples all over science. These things, I don't know, I just took these things off Wikipedia. I've got no idea what any of those things mean, but they look very important, so I thought I'd mention them. So this one, I do know what it means. Decrypting data sets. We have a standard way of sending data to a secure website. To secure website when we're typing in, typing in credit card numbers to buy things on the internet, and decrypting that without the decryption key is something that we don't know how to do very quickly, but as I say, it's in NP. There's various other things. Candy Crush is an MP. Pokemon, also an MP. Super Mario Brothers, also an MP. Basically, trying to solve a Super Mario Brothers level is very hard, but if someone comes along and if somebody comes along and does it, you can clearly check that they've done it because they've got to the end. So we don't know a fast method for solving any of those problems, but we know a fast method for checking the answers. So there's examples of problems that are in P, but we don't know they're in NP, but we don't know if they're in P. Okay. So there's the question: does P equal NP? If we can check, if we have a problem and it turns out we can check to see if the solution is correct quickly, can we actually have solved the problem quickly in the first place without knowing what the solution was? I'm doing all right. I thought I was going to overrun. I'm doing great. So there you go. By 1971, Stephen Cook had formalised this notion, and he raised this question explicitly in 1971, having laid down some mathematical background. So he'd given a rigorous mathematical notion of what a problem was, or what a solution was, and the class of problems that are in P and the class of problems that are in NP. There's lots of mathematics and rigour that I'm suppressing, but he did it, and he raised this question explicitly. And then the year after, he failed to get tenure at UC Berkeley. And because computers in 1971 were really irrelevant, right? So it's an abstract, well-defined mathematical question, and it was an unsolved problem that the mathematicians at UC Berkeley decided was of peripheral interest. But you've seen now the kind of implications that solving this problem might have. And it's now regarded as one of the most important problems in mathematics. It's one of the 7 clay millennium problems. So if you solve it, some entrepreneur has donated $1 million as motivation for trying to solve this problem. Turns out, so that's what it looks like. We've got the problems in P, they're in there. We've got the problems in NP, and then the question is there actually definitely a problem that's lurking where that question mark is? That's in NP, you can check the answer quickly, but it's definitely not in P, right? So we know plenty of problems that are in P, and we know plenty of problems that are in NP, and we don't know if they're in P or not, but that's the current state of our knowledge. Okay? So what would happen if somebody proved that P equals NP? Because mathematicians, theoretical computer science is working very hard on this problem. What would happen if somebody proved P equals NP? Then all of a sudden, a whole bunch of problems which we didn't know how to solve, suddenly we could solve very, very quickly using a computer, right? So suddenly transportation gets scheduled optimally, we save lots of fuel, people and goods move around quicker and cheaper, factories become infinitely more efficient, dramatic advances in medicine, because suddenly we can, cure cancer. I don't think we can cure cancer, we would certainly we can certainly do much quicker experiments. Perfect computer vision, computer language recognition. So you see the problem, it wasn't very important in 1971, but better predictions of weather and of earthquakes, huge advances in modern mathematics, because solving a mathematical problem is a great example of something that's in NP. I work on a problem, I can't do it. There's lots of axioms, I don't know how to apply them or what orders to apply them in. But if somebody comes along and hands me a proof of this, if someone says, I can prove the thing, I can sort out the thing you're working on, here's the question you're working on, here's a proof of it, I can read the proof really quickly. I can check that that's a mathematical proof. That's kind of part of my training. So I can check the answer. So we can just get computers to do lots and lots of modern mathematics. It also means, of course, that there's no such thing as encryption anymore, so the government can read all your emails, even if you encrypt them, and internet security is now broken. You can't type your credit card into the internet, so online banks instantly, everything gets stopped. So society really changes. The internet stops working, but maybe we can cure cancer. So but the world would be a very different place. Unfortunately, or possibly fortunately, most computer scientists believe that P is not equal to NP. They believe that there are problems out there which are easy to check but hard to solve. Easy to check the solutions but hard to solve. So what would happen if we proved that P was not equal to NP? Then we know we have algorithms which we now guaranteed can't be solved quickly. Now we definitely know we can talk in code. So I know that the government can't spy on me. That's really good. And terrorists also know that the government can't spy on them. And all the people that are currently selling illegal drugs and weapons on the dark internet, and that really is happening, they can sit comfortably knowing full well that they can definitely not be traced. So again, the world changes a little bit, and this is currently the working model, right? Theresa May was very, very upset about this. There was an iPhone story, you remember this? Some guy, there was incriminating evidence on his iPhone, but they couldn't unlock it, and Apple said they weren't going to unlock it. And the problem resolved itself, but that's the tip of the iceberg. More will happen again. There will be police officers that know full well that there's an encrypted drive that if they could decrypt, then this guy is nailed, but they can't decrypt it. If P is an MP, we can design codes that are going to be impossible to break. So it should be clear that it's clearly important to work out if P is MP or not, right? So all the problems in P are in MP, but the question is, are there problems in MP but not in P? Where am I? I thought I'd finished. If you tell me the solution to a problem in class P, I've said all this already. So how? No, this is the point. Sorry, I'm going to tell you the point. How is a mathematician? So P probably isn't equal to MP. So how's a mathematician going to prove that? Right. And this is the point. All they have to do is they have to find something in that question mark. They have to find a problem which is in NP. We can check the answer quickly, but they have to prove that this problem cannot be solved quickly. That's what the problem is. And we're not yet at the stage where we have the theoretical tools to do that. This is the issue. We have to prove that you can't do something. And we could only prove you could do things in the 70s, so when are we going to be able to prove that you can't do things, right? So here's the time frame now, the third example of doing things and not doing things. Nash, formulated the question, gave easy examples of problems that could be solved quickly. Cook formalizes the mathematics, raises the question explicitly, and then we don't know what happens, right? Somebody at some point probably will find an example of a problem where they can check answers quickly, but they can prove that you cannot solve it quickly. But we are not yet there. It took 2,000 years for the Euclid one. How long will this take? So many modern mathematical techniques have been tried, all have failed. So it's a technical thing. There was a promising approach developed initially in 2001 and then really prominently in 2011 using geometric complexity theory. And again, it follows exactly the same pattern as the other things. This used modern algebraic geometry, which was only invented in the 1960s, and modern representation theory. So using these very, very modern techniques that weren't around for people like Cook and Nash, geometric complexity theory was an attempt to resolve this question. But the big breakthrough in April last year was a team of people proved that actually the path that we were following using geometric complexity theory to prove that P was not equal to 1P, they proved that it would not work. So you see, mathematicians are good at proving that things don't happen, but in this case, it wasn't proving that P wasn't MP, it was proving that our idea is even sort of meta, right? The strategy of proof cannot succeed. So there you go. So that's the end of the talk. How do we prove that computers can't solve a problem quickly? Currently, we don't know the answer. But, so thank you.
Good evening, everyone, and thank you, John, for that very kind introduction. And of course, thank you to the Royal Institution for giving me the opportunity to talk in probably the most magical and famous lecture theatre in the world. My friend told me this morning that the electron was announced here 11 chemical compounds were discovered here, and I looked at him and said, no one's perfect. It's okay. Anyway, as John said, I'm here to really take you through a journey of surgical scientific innovation from the times of Joseph Lister in the 1860s all the way through to modern times, where I'll be discussing minimally invasive surgery, robotics, 3D printing, machine perfusion of organs, and I'll be using my own speciality of organ transplantation to illustrate that journey, but of course the principles can be transferred. But before I begin, I must pay a tribute to one of my heroes, and indeed the heart and soul, if you like, of the Royal Institution, Michael Faraday himself. Now, Faraday lectured here, and I'm very lucky today because Charlotte from the Royal Institution of Archives has actually given me, for the purpose of this talk, Faraday's original apparatus. So this is the induction ring, and this is the electric generator. And these are original instruments that Faraday himself created and used to demonstrate, if you like, how magnetic fields and electric fields interact to produce the electromotive force. This is the invisible energy, if you like, that we can't see, but we can see the effects of. And why am I mentioning that? Because Faraday lives on in medicine. So this humble man working away in the basement here at the Royal Institution, working with laws of nature, potential, are using medicine every day. So, for example, CT scans, MRI scans, using the principles that Faraday laid down. In surgery, when we use things like dialysis, they can go through tissues and stop blood vessels bleeding using the principles that Faraday laid down. So comparing generator here, very important, is this machine designed to be power. And of course, when we're headlights, of course, uses Michael Faraday's principles as well. So, humble scientists working here with very, very simple-looking instruments and apparatus really would serve their purpose many, many decades later. So, from one great scientist to another great scientist, the name of Joseph Lister really is associated with safe surgery and global health worldwide, and his name really carries a huge umbrella, if you like, and has influenced medicine all over. Now, Lister was born in 1827. His father was a fellow of the Royal Society as well for the invention of the achromatic lens. He trained as a medical student in London, had a nervous breakdown on the way, then went up to Scotland, where he became Professor of Surgery in Glasgow, the Regis Professor, and then in Edinburgh, and then he eventually came back down to London to my own university, actually King's College, where he was Professor in 1877. Now, Lister's multidimensional vision, not just with the antiseptic principle, but with respect to surgical innovation, research, education, has managed to elevate and steer the craft of surgery towards higher standards. And those legacies are still important now, as they were 150 years ago, in progressing science. But let's think about the problems that the young Joseph Lister was facing in the 1860s. Let me ask you, the audience, what do you think your chances are of surviving an operation in the 1860s? Imagine you have a fractured leg, hit by a car. That wasn't quite a common method of injury. Practically zero. Okay, well, it's not that bad. It's actually about 50%, so the odds are against you. And the thing that would kill you was infection, overwhelming sepsis. So what did the young Lister do about this? Well, all of a sudden, in 1867, a paper appeared in the Lancet. So it's one of the world's best medical journals. And the author was a young Regis Professor of Clinical Surgery, a Fellow of the Royal Society, age 32. And in this paper, I encourage you all to read it, he described the meticulous treatment of an 11-year-old boy that came to Glasgow Royal Infirmary, sustained a fracture of his tibia, and he treated it with tartaric acid, and the boy left hospital 6 weeks later. And with a further 11 cases reported, Lister claimed, essentially, that the mortality on his wards improved from about 45% to 15%. But this landmark paper really, if you like, is the embryo of the antiseptic principle, which then became the antiseptic system in the practice of surgery. So, and as I say, I encourage you all to read it. It really is a fantastic paper. Now here's Lister's first 11 cases, courtesy of Professor Harold Ellis. So it looks like Lister was an orthopedic surgeon to me. I don't know what it looks like to you, but look, it's all bone here, essentially. And look at the mechanisms of injury. Cartwheel, horse kick, head box, omnibus wheel, quarry, engine button, jump out window. Yeah, we often feel like that sometimes, but that's okay. So you can see that Lister, basically, it's an impressive series. I mean, 11 cases, and 2 of them died. But Lister had great insight into auditing his outcomes. An important principle even to this day where surgeons are responsible, transparent, and accountable for the surgery that they do. Now, the background to Lister's work is well known. He studied the works of Louis Pasteur on fermentation and germ theory and showed that tissue destruction through infection essentially could be prevented by germ exclusion. And this led to the development of the carbolic spray. Now, I've actually got an original carbolic spray here, lent to us by Bill Edwards from the Gordon Museum at Guy's. So this is a Listerian carbolic spray. I don't know how it works. But essentially, it was used to vaporize the anatomical part of the body that you're interested in operating on. And surgeons would actually dab their hands in carbolic acid. And they said that you could actually tell a Listerian surgeon just by shaking his hand, because the hands get quite rough. But the reason, I mean, it's not a very pretty looking object. You can imagine patients would be quite scared actually of seeing that when they were walked into the operating theatre. But in those days, it was a bit like this theatre. The patient was in the centre, the surgeons would be around them. This would be full of medical students and doctors in their normal clothes, straight from the streets of London. And all this naked array of steel would be around them. So it's quite a frightening environment. But fundamentally, this object represents an important principle in surgical innovations, because what it represents is Lister's attempt to change the way in which a surgeon would think about an operation, to try and be more in control of their outcomes by controlling infection. It's a paradigm shift towards scientific surgery. In other words, Lister was using this as a tool to carry out a surgical scientific intervention for the purposes of clinical benefit, and that's something that we do all the time. So Lister's antiseptic principle eventually developed global appeal. It resulted in a surgical explosion, if you like, of operative repertoire. So by 1900s, nearly all parts of the body were at least being attended on with respect to surgery: the brain, the chest, the abdomen, the pelvis, as the concept of asepsis now began to emerge. So, let's fast forward 150 years, and it's a combination really of Listerian principles and our increased understanding of patient care before, during and after surgery that has led to improved surgical outcomes. As these landmark papers published in the New England Journal of Medicine, the world's best medical journal, have shown that the more a surgeon operates, especially in a high-volume hospital that's repeatedly doing operations, complex operations, the less the risk of dying. So there's a strong association between volume, surgical volume, and hospital volume, and operative risk outcomes. And that's across all 4 of the major cancer operations: esophagectomy, pancreatectomy, lung resection, and bladder removal, and also for the cardiovascular operations. So that's all very encouraging. But the modern surgeon still has challenges. Now, Lister dealt with infection. We still deal with infection. In 2010, a landmark published paper in the New England Journal of Medicine compared chlorhexidine with iodine with a randomized controlled trial. So patients were randomly allocated to one of these 2 antiseptics. And this one won. 41% reduction in surgical site infections with this. So we're still really investigating things that Lister was investigating, but the modern surgeon still has problems. We have to operate on extremes of age: very young, very old. We have to operate on complex patient mix. So, for example, patients presented with very advanced diabetes, or very advanced cardiovascular diseases, or very advanced cancer. We've got to try and innovate to make things as minimally invasive as possible, and I'll be touching on that later. We've got issues in transplantation. Again, I'll be touching on that later. Resistant bacteria, huge problems. And of course, cancer surgery and trauma reconstruction, especially with respect to military surgery, are all challenges facing the surgeon. So I'm going to concentrate now on the first 4 of these. So let's just think about which operation is best. And that's how I look on a bad day. So is it the open operation, the laparoscopic operation of the robotic operation. Now, to do this, I'm going to take you back to the 1950s. That's when surgery was still performed mostly in the open fashion. Now, you're probably wondering what this is about.